all of the arguments which say that time's arrow is determined by the growth of entropy is just only applies. You have, first of all, have to assume that for some inexplicable reason you start off with a very special ordered state, and that state is confined, it's in a box, and it can't help equilibrating, and that will create narrow time. Then you look around at the universe and you see that it's way out of equilibrium, and when you then look at what Newton's theory of gravitating particles tell you, then it's no mystery at all. That theory tells you the universe will seem to have started in a very uniform state and become structured from then on. That's just sitting in Newton's theory. And I think this is bound to change the whole discussion.
Hello, my geeslings. This is Mother Goose Robinson Erhardt here with the introduction to Robinson's podcast, number 121. And this episode is with Julian Barbour, who is a physicist working in the foundations of physics and quantum gravity, who also has a special interest in time and the history of science. And Julian and I start off with a discussion of time's arrows. So note the plural here. This is more nuanced than just the lay conception that you and I probably share of a single arrow of time moving from the past to the future. And then we go into a brief history of thermodynamics, because entropy, so the tendency for systems to move from order to disorder, has long been proposed as the feature of the universe that gives time its direction, while the other laws of physics are time reversal invariant, which means that they work equally well both backward and forward. And from there, we move on to Julian's new theory of time, which centers around the notion of a Janus point, which is a phrase he coined. And though it's more nuanced than this, the rough idea is that there is a point in our past from which not one, but two arrows branch off, each moving from this common point to their own separate futures. And there are also models that we talk about in which only one arrow branches off from this past, and that more closely resembles the picture we all have of the Big Bang. But this is the rough picture of the idea of the Janus point, and of course we get into much more depth about that. We also talk about some other interesting areas of cosmology, notably inflation, and then we talk about some quantum mechanics here and there. So there's a lot going on in this episode. It was really fun. And one caveat worth mentioning, though, is that there's a little bit of lag in our recording. So there are a few moments in which we talk over each other, though I have done my best to edit this out. And in the description, you'll find links to Julian's website, to the Janus point, which is his book on these subjects that we are discussing, a link to a history of thermodynamics that Julian wrote and is available free as a PDF from his website, and then also a paper he wrote for a Festschrift in honor of David Deutsch that we get to toward the end of the episode that identifies some redundancies he sees in quantum theory that might allow for the elimination of the wave function altogether. So reviews, comments, likes, subscribes, these are all endlessly appreciated. And then there is my channel on Twitch and YouTube. And now perhaps Kick, Robinson Eats, in which I, at this point at least, am eating a pint or so of, or some quantity of frozen confections commensurate with a pint, live streaming every day if you want to join me for that. So without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Julian. As I was doing some preparation, I saw that your graduate work was focused on general relativity, and that made me wonder whether, since time is going to be the main subject of our discussion today, whether time has always been the concept in the foundations of physics that gripped you most.
Yes, I mean, that happened just before I did my doctorate in Germany. It all came out purely by chance. In October 1963, I happened to read an article in the Munich newspaper about the only popular science article that Paul Dirac, the great quantum physicist, had ever written. That was in the Scientific American in 1963, May. And he was talking about work he'd done in 1958-59, trying to understand general relativity, not as a space-time theory, but as a dynamical theory. And he'd wanted to do that to make it a proper make a quantum theory out of it. And very important for that, he wanted to get general relativity into a form in which only the physical quantities appeared and nothing that was sort of just to do with the way it was represented. And he found that the only way he could do that was to reintroduce a notion of simultaneity. And this surprised him very greatly. And he wrote his very short paper in 1958. About 7 times he repeatedly said that he did not believe that four-dimensional symmetry is a feature of the physical world or a fundamental feature of it. And that really impressed me, and it prompted me to start thinking, well, if Dirac thinks there is a notion of absolute simultaneity, what is time? And I'm still thinking about it now. And then I found that other people, I wasn't aware that more or less just at that time, a major problem was arising in the attempts to quantize general relativity, where time seemed to disappear. And I now see that it was very closely related to what Dirac was saying and thinking.
Well, maybe the notion of simultaneity will emerge again later in our discussion. But for the moment, the Janus point, your most recent book that we're about to be discussing, is about, among other things, the direction of time. And most of us are familiar with the idea of time's arrow in the singular, namely that it points forward from past to future. But you are careful to refer to time's arrows in the plural and to disambiguate them. And maybe we should start by discussing the 3 that you take to be most salient. So let me ask first, what is and how do you describe the arrow of equilibration?
Well, that's what really came to the fore in the 1850s, immediately after the discovery of the first 2 laws of thermodynamics in 1850. And that fairly soon within the next 10, 15 years led to the very precise concept of entropy by Rudolf Clausius. To define it precisely, he had to assume a system that was always in equilibrium and was being moved very carefully, reversibly from one equilibrium state to another. But the very easy way to think about equilibration is if you start off with a sealed box, and in one corner of it there's a small cube of ice, and there's air in the box. Well, bit by bit, first the ice will melt, and then it will evaporate, and the water molecules will be spread out uniformly over the entire box. Now, the original arrangement of the water molecules in the ice is a highly ordered structure. It's a crystal lattice. And then after that, it's all spread out. So this is the paradigmatic example of growth of entropy to maximal entropy, where it's fully equilibrated, and that's that, so to speak, that's what one thinks of as heat death. And this made a huge impression. So in 1865, when Clausius actually coined the expression entropy to make it sound like energy, so the two fundamental concepts that he'd identified were energy and entropy, he said very proudly, I can now formulate two laws of the universe. The energy of the universe is constant. The entropy of the universe tends to a maximum. And by and large, I would say the great majority of physicists ever since then have accepted what Clausius said. And I'm very skeptical about it because a key part of making it all seem so clear is that I started off with having that bit of ice, that block of ice in the corner of a big box. And if it weren't for the walls of the box, the molecules would just escape off into space. If that was happening out in space, for example, there's no way you would get that equilibration. And I think a lot of the discussion of entropy has just come about because people haven't thought about how it was originally discovered and formulated.
Mm-hmm. Now, just parenthetically, among many things I love about your book is, the first thing, this isn't what I was going to mention, is that I think the phrase you use is you refer to yourself as a buff of the bard. You're a big fan of Shakespeare. So Shakespeare is constantly making appearances. I actually just finished the book this morning, and I very much appreciated Gerard Manley Hopkins' appearance at the end of the book because he's another figure that I love. But what I was going to mention is you also have a taste for etymology, which I do as well. And you just mentioned Rudolf Clausius's coining of the term entropy. And maybe you could say a bit about the etymology there because it is fascinating.
Now, trophy, well, it comes from the Greek trophy, which, if I'm not mistaken, it just means transformation. He originally called this quantity the transformation value. And then he just added the EN to make it sound like energy. He's quite frank about that. I think that's correct, yes. It's sometimes since I'm relying on my memory, but I do find etymology is very revealing. It's very, looking at it, it's very helpful to see how concepts come into existence, and particularly right at the start, very recently, very interestingly, I did know about it, but where the word, what chaos originally meant. Chaos originally it first appears in the very early Greek poet, the contemporary of Homer, Hesiod, where he's talking about the gods. And he says that in the beginning there was chaos, and it really means a gap between something that bounds it, and the word chaos is related to our word yawn. And
really?
yes, that I was aware of. And so it's actually sort of 500 years later before the word chaos in the modern meaning comes in Ovid, the Latin poet's work. And in Hesiod and in the ancient Greeks, it just meant really a gap between some boundary, which is very revealing, I think. And I heard about this in a talk in Oxford a month or so ago, and I commented that the most fundamental, the original dynamical law, Newton's law of gravitating particles, it's all about a gap between particles. So that's the boundary which Hesiod talks about, and the space between, the gap, the void between.
Do you see the relationship between this boundary this notion of gaps between boundaries as reflecting in mathematical and physical conceptions of chaos, in which there's this huge disparate boundary between initial conditions and the plethora of later conditions that result from the sensitivity to the initial conditions. There's just this huge gap between the results, or that's not how you see it relating to the etymology?
I think there could be. So I'm not quite sure how, I did put it in the Janus point, but I think it's I'm emphasizing it much more now. So if you're thinking about a physical system, in a laboratory, you can just put a gas in a box and that's it. And so it's either confined, or if it escapes, it's unconfined. However, on the Earth, the gravitational force always keeps us on the Earth. We can't escape from the Earth, well, only with a rocket. But in mathematics, there's a distinction between the key concept in dynamical theory is the phase space. Each phase is defined by all the positions of the particles and their momenta together. So that's a huge multidimensional space. And the dynamical solutions can explore either a bounded region of it or an unbounded region. And what I'm coming more and more to the conviction is that these two situations are very, very different. And there are this workshop that I attended in Oxford a month or so ago was very interesting. There were 3 talks. One was on chaos, one was on entropy, and one was on complexity. And it became clear to me that all of these, they were very good talks, very interesting, but in all cases, the discussion was about situations where the objects were confined. They couldn't go out all the way to infinity. But the oldest dynamical theory we have is the Newtonian n-body problem. It's the problem of a finite number of gravitating point particles. And the scale in the Newtonian representation, the scale of that system can go to infinity. And it's just quite different. So I think the two situations are as different as day and night, black and white. And the great bulk of all the work that scientists have done is about systems that are confined, that the technical expression is their solutions only explore a finite region of a region with bounded Liouville measure is the technical term. And it's going to be just quite different. So the question is that an appropriate framework to think about the universe? And I'm getting increasingly of the conviction that that's not the case, that it's quite different.
Well, boundaries will become very important as we get to the recurrence theorem and cosmic inflation. But for now, I just would like to also note that as fun as the etymology of entropy is, one of your collaborators, I think, Flavio Mercati, if I have the name correct, pronunciation correct, also coined a neologism, entaxy, that we'll also get to later, but that is a correlate maybe of entropy. But just to paraphrase before we move on, so the arrow of equilibration is within a closed system, a highly ordered state will move to one of disordered equilibrium. Is that a decent paraphrase? Okay, great. And then there's another arrow which you point has a somewhat funny name, but it's an arrow associated with retarded waves.
Yes.
Could you explain that arrow?
Well, that just comes from the fact that a radio antenna or TV antenna sends out signals, and they go out in principle all the way through the universe. They never come back going in towards the antenna. and that's called the radiative arrow of time. I'm inclined to think that that's just another example of what I was saying about the thermodynamic arrow, because if you were if this was happening in a box, you'd quite soon get a chaotic situation. In fact, actually, now I think about it, the best microwaves are constructed so that the electromagnetic energy is distributed chaotically within the microwave, because then you don't get these hot and cold spots in the microwave. So I think, I suspect that really the radiative arrow is just another example of what one would call the growth of entropy in a confined region. I don't think that's I think I rather skipped over the radiative arrow in the book. I only just mentioned it, but I think at the back of my mind there was already something like that. But now I think about it, the microwave ovens is a very good example of saying, well, it's really the radiative arrow is just the same as the entropic arrow.
Okay, and then the third arrow, and then we can be finished laying out the arrows, is related to wave function collapse. And I don't think that this, well, maybe you will relate it to the thermodynamic arrow, but how do you think of this arrow?
Well, it's a notorious arrow in quantum mechanics, and I guess it's related to the famous problem of Schrödinger's cat, which can be in a state of being alive and dead. So you can imagine that it's in a box, and it's both alive and dead until you open the box and look, and then it's either alive or dead, and that's what is the collapse of the wave function. And it's basically that problem which leads virtually all physicists to say that quantum mechanics is the most fantastically well-confirmed theory. There's a very precise theory of quantum mechanics. All the experiments confirm it. The technical applications are just unbelievable. I mean, we couldn't be talking to each other without very good understanding of engineers of how to do all these things, and it all goes back to quantum mechanics. But yet, at the end, everybody says they don't understand it at all. Now, in the Janus point, I don't think I made any sort of attempt to grapple with it then. But since then, because of a suggestion I made in the Janus point for what time might actually be, some of my collaborators and I have come to the conclusion that there may not be any wave function at all. We might get around to talking about that later.
Oh, really? So you're the exact opposite of the Everettian.
If that's, well, I was already getting skeptical about the many worlds interpretation before this, but I think we'll leave that for a little bit later in the discussion.
Okay, sure. No, that sounds good. I think the next logical place to move, though, is the problems that these arrows pose for physics and the time reversal symmetry of physical laws.
Yep.
What is the main problem that these arrows pose?
The main problem is that certainly Newton's laws and all of the laws of nature that one would imagine could be significant don't distinguish the direction of time. They work equally well in both directions. So the situation in, shall we say, in Newton's theory is you imagine the particles starting off in a certain state with certain velocities or certain momenta. The momenta are just the velocities multiplied by the mass. And they evolve quite beautifully. And then you could imagine stopping the particles, keeping the positions that they've reached, and exactly reversing the velocities. And then, according to Newton's laws, they will just go back the path that they came, and they will go back to the positions they had before, but going in the opposite direction. And that's called time reversal symmetry. And that's also true for Einstein's general theory of relativity. It's true for Maxwell's theory of electrodynamics. In the last 50 or 60, I can't remember exactly when it was, tiny violations of time reversal symmetry have been found in particle theory. They're very, very small. They are mysterious, and they may well be significant for why there's matter in the universe as opposed to no matter at all. But nobody thinks that they have any real influence on the direction of time, the sense of the direction of time. So that's the problem of time reversal symmetry.
And now is where entropy comes in. And there's a tremendously rich history of thermodynamics. I think, in the Janus point that, at least at the time of publication, you were planning on writing a second book or another book just on this history, because your editors thought that you put perhaps too much into the book, so you had to cut it out. But I really loved the portions that were there, because Clausius, Boltzmann, these are all tremendously interesting characters, and all the discussion of steam engines and the
but my editor did a good job. In fact, what happened is I just cut out a whole hunk of, I don't know how much it was, perhaps 100 pages, and just they're all on my website. And quite a lot of people have read it and said, do extend it a bit more and make a book out of it. But the trouble is I'm trying to do so many other things at once. I'm not sure I'll ever get round to it, but they are on my website. I mean, perhaps it might be even more sensible just to put them on the archive, which you can do now, and then more people perhaps would have access to them. I've no idea how many people have looked at them, but at least one or two interesting people have read them, and I've got into contact with them. A very, very nice Indian student they contacted me about them, and we've talked on Zoom every now and then. So it's out there, but the editor was T.J. Keller was quite right that I'd put too much history in at the start.
I will put a link to this area of your website in the description for anybody who wants to look at the detailed history. But I don't know if you think it would be worthwhile now to discuss something like a potted history of thermodynamics, or if we should just get into how entropy might, or how people have thought or attempted to use it to account for the temporal directionality of physics in the universe.
The first two laws of thermodynamics were both discovered in 1850. The person who got in first and published it was Rudolf Clausius. And for the second law of thermodynamics, he just pointed out that heat flows spontaneously from a hotter to a colder body, but not in the opposite direction. And that was the first precise observation that underlay the development of the second law of thermodynamics. And then very quickly, it was Helmholtz in Germany who coined the expression heat death. So heat death was a concept by 1855. Meanwhile, Clausius was working away on his precise concept of entropy, and in 1865 was when Clausius made those two notorious statements that I mentioned. A person we should mention, and I didn't mention nearly enough in the Janus point or in what I put on my website, is the work of Gibbs in the United States, who did marvelous work. Einstein in a way rated him even higher than Boltzmann. And Willard Gibbs is his name. And he just did fantastic work. And I think you can say he's the founder of sort of physical chemistry. He developed things in such a way that a huge amount of scientific applications, engineering applications, go back to the work of Gibbs. And all of that relies on the equilibrium state. And in fact, a huge number of scientific discoveries were made in thermodynamics and statistical mechanics from the properties of systems when they are in equilibrium. So that led to the first reliable predictions of the number of molecules in a gram, what the size of the molecules are, what the, things like that. And then finally, it led on in 1900 to the most amazing discovery, the first discovery of quantum mechanics by Planck in 1900. So all of this putting systems in a box was extraordinarily effective. In fact, I recently, a few months ago, I published a paper called Gravity's Creative Core, in which I mentioned the British, the English philosopher and politician who, what's his name now, in Queen Elizabeth's time. I'm getting terrible in remembering names, but he said that he's reputed to have said that you had to torture nature to get her secrets. And who was anyway? It may come to me before I finish. My brain continues to work very well for the physics, but for the names some have read, it's not so good. Let me just continue though that story. So
I'm just looking it up.
He said that. Okay, you'll come in a minute.
Bacon?
It's Bacon.
Yeah.
Francis Bacon. Francis Bacon is the man. Yes. And he apparently, really, what he was saying, that we had to struggle with nature to get its secrets. But I very much like the idea of torturing nature, because in fact, what physicists did in the 19th century by putting physical systems in a box and studying them in equilibrium was in a sense, you can say, putting them in the box was putting them in prison, and then increasing the pressure or the temperature or so forth. Those are like the screws when you torture someone. And this indeed, out of this torture, nature did give up most amazing secrets. However, the final thing, nature got her own back by saying yes, and the reward for all that is heat death. But in fact, I think I can finish in that thing. I do recommend anybody who's interested to read that. It's on the archive. It's Gravity's Creative Core, and I say, well, maybe you have to let nature free, let it explore the whole of all the possibilities, and then you see that actually structure comes. It's just completely different, I believe, between a system which is essentially confined and in a box, metaphorically speaking, and one that can explore all possibilities. And so I quite like that conceit, as one calls it, of nature getting her own back for being tortured and giving up all those secrets, marvelous as they are.
And just for our listeners who aren't familiar with this term, heat death, it is, as far as I'm aware, and maybe you can put a more precise gloss on it, but going back to this arrow of equilibration, the idea is that as time goes on, the highly ordered state dissipates into something approaching equilibrium, so that as time goes on in the universe, these ordered structures like stars or people will slowly disintegrate to this uniform state where atoms are just moving about randomly and hardly ever touching each other as the universe expands.
I guess that's more or less how people think about it. Personally, I think there's a lot of issues related to black holes and things, which I would say is still a bit open.
I thought that with
certainly for
sorry, I was going to say that I thought that with
systems in a box.
Hawking radiation, the black holes would also dissipate because they will slowly lose mass.
That's what Hawking's theory, and it does seem to be fairly secure. But there's mysteries about Hawking's work, and I would say I'm not really. I wouldn't pretend to have too much expertise in that. I only read things about it. There is a thing, because the universe is now observed to be its expansion accelerating, that leads to another effect, which is a bit like putting the whole universe in a box. It's when you sort of, things disappear because they're moving away so fast. And that is why, for example, Sean Carroll argues that the end state of the universe will be entropic. Now, that may be the case. I think I may be wrong. Maybe that is right. But certainly, I would say it's still uncertain. There's so many puzzles in cosmology. I mean, cosmologists they have great difficulty really in explaining how structure comes. There is a theory of inflation, but I think people are getting progressively more uncertain about it. And now there are major differences, a thing called the Hubble tension, where there are two different ways at which you can deduce a very important quantity, the Hubble constant, and they differ by about, I think it's 6 or 7%. That's a significant thing. Then the biggest one of all is that physicists can observe and understand only something like 6 or 7% of the matter in the universe. There's about a quarter of the matter is in dark matter, they think, and then the rest is in dark energy, and they haven't any idea what either of those are. So, I mean, at the moment, cosmology is in a way, there's a very fine theory, a concordance model, which gives very precise results, and you use only 6 or 7. There's a very nice book by Martin Rees, Just 6 Numbers, which go into a model to explain it. But where those 6 numbers come from, some of them are utterly impossible to understand, and others are a bit sort of put in by hand. So I think it's just too early to say.
You mentioned Sean Carroll, and you also reference him many times in your book. I'm a big fan of Sean's, and he was recently on the show a few weeks ago, and we're doing another episode in a few days. But that episode a few weeks ago was a joint episode where I spoke with him and David Albert, who you also discuss in your book. And I think this might have come up briefly in our conversation when we were discussing entropy and fine-tuning, but I don't know if you and I will end up getting to fine-tuning. But you reference David Albert's past hypothesis, which I think reflects something that Boltzmann might have put 100 years earlier. But what is David's past hypothesis? Why is it so relevant to the arrow of time, or the arrows of time that we've been discussing? And why does it fail?
Well, it's just put in desperation, because if you really believe that there's an entropy, that you can meaningfully define an entropy for the whole universe, which I'm not at all persuaded you can, but if you can, then already Boltzmann said one way to explain why the universe is not in equilibrium, why it's so far out of equilibrium. We couldn't be talking to each other if the universe weren't very far from equilibrium, is if the universe did start with a very low entropy. The first person who really said that absolutely clearly, and that you had to put in such an assumption in addition to the known laws, is Richard Feynman, whom I do remember I cited in the Janus point. He said that, for some reason which we do not know, we have to add this additional hypothesis or this additional assumption, which is not sitting inside the known laws. And then eventually this was given the name the past hypothesis by David Albert. Roger Penrose, in his Emperor's New Mind, was also saying that. But Feynman, I think the first really clear modern statement is by Feynman. But by the way, he makes it in conditions which makes me really suspicious, because he starts off with talking about atoms in a box, and he talks about fluctuations. That was an idea that Boltzmann had. He had fluctuations, and then he goes from atoms in a box to talking about the whole universe. And I think he's just still thinking that the universe is in a box. And so I must say, I just think everybody who writes about it, they all just instinctively are still thinking in terms of steam engines. Thermodynamics was discovered after this marvelous book by the Frenchman Sadi Carnot in 1824 on how you make steam engines run with maximal efficiency that is possible. And if the steam escapes from the cylinder, the steam engine will stop. And I think this is, I don't think people who write about all of these issues have just shaken off that assumption. I think it's very remarkable. I mean, I've looked at a lot of the literature on the arrow of time and entropy and all of these things. I have not once seen anybody emphasize that this could completely change the things. I haven't seen it. If you can come across anybody who says that, or you could ask Sean for it when you next talk to him.
Well, one last thing that I wanted to touch on regarding entropy is a topic of enduring fascination, even though I think it's probably largely tangential to our discussion of time, and that is the notion of the Boltzmann brain, which you do cover in the Janus point. But for our listeners who aren't aware of what a Boltzmann brain is, the idea is roughly that if the universe continues on indefinitely and atoms continue bouncing around indefinitely through either quantum or thermodynamic fluctuations, there should, over time, randomly, though rarely, spontaneously occur or manifest observers, brains basically, that can have the belief that they are observing a universe, something ordered like ours. But the issue is that if these arise rarely, but the universe goes on indefinitely, there should be infinitely many more of those than there are of our real, quote unquote, naturally arising brains. And I'm wondering how you think of Boltzmann brains and how you deal with them, because they've been a gadfly for physicists and cosmologists.
Yes. Now, I've definitely got ideas about that. So it goes back to a suggestion that Boltzmann wrote a letter to Nature, the English science journal, in, I think it's 1895, in which he talks about the arrow of time and entropy, and he suggests, and he doesn't even say it's his own idea, he puts it down to his assistants, his laboratory assistants' idea, that the universe is perpetually in thermal equilibrium, as one would expect, but that every now and then there are just fluctuations, and Boltzmann conjectured that they would be really substantial ones, the size of a galaxy or more. And at the time Boltzmann said that, many people thought that our galaxy was the entire universe. And then he said that could come into existence, and would then the entropy in that fluctuation would then increase. And he said that the past would always be, we would always regard the past as being where the universe was most ordered. And I think it's at that point, or certainly around then, that Boltzmann says quite clearly that we get our sense of the direction of time from the growth of entropy. So then, what then happened, I think it was in 1931, or it might have been a little bit earlier, Arthur Eddington, the English astronomer and the man who'd made Einstein a world celebrity overnight with his famous telegram to the Times in 1919, he said, well, actually, rather than a fluctuation which creates the whole of the galaxy, it would be much more likely that it would just create this group of people to whom I'm speaking at the moment in this scientific meeting somewhere in London. And then a year or two later, the two Russian scientists, Bronstein, who was a significant figure, early person trying to develop quantum gravity, and Landau, the famous physicist, they put out a paper saying, well, the much more probable thing would be just a single brain that comes into existence, and so forth. So that's, I think, in 1933 or 34 at the latest. And then I think it is Sean Carroll, about 2001, who coined the expression Boltzmann brain. Now, all of that is okay if you're in a box. But my title of my book, The Janus Point, comes that things look very different, that within Newtonian theory, there are strong indications that that's not the way things happen at all, that actually the way you should think about there's two possibilities, but in both cases, people within the universe would experience an arrow of time. They would experience laws of nature which are time reversal symmetric, and they would think that the past was more disordered and the future more ordered, the exact opposite of that. And that, again, just comes about because in the Newtonian theory, it's not in a box. The gravitating particles can move apart. And then it just follows directly out of Newton's laws. If the energy is non-negative, it's either zero or positive, and there's a strong argument for saying the energy should be zero. Then there's always a state when the universe is more uniform and later becomes more structured, or along the timeline, and the natural direction is along the direction in which the universe gets more structured. And that's what it's a dynamic explanation of the arrow of time. It's not an entropic one. And this was first appeared in the paper by myself and my two collaborators, Tim Kozlowski and Flavio Mercati, whom we've already mentioned, in a paper which was published in Physical Review Letters in 2014. And it's quite interesting because this was, I think, the very first paper which showed that there could be a dynamical arrow of time. Nothing whatever to do with statistics, nothing whatever to do with entropy. And in fact, the possibility of it that people could have realized it had been sitting there for 200 or 300 years because it comes straight out of Newton's theory. Physical Review Letters, actually, they obviously thought they had to better be careful with this because they sent it to 5 referees. One of the referees just said, this can't be published because it's wrong, but gave no reasons. Another referee said, well, they've only established 1 arrow of time. That's not enough to publish the paper. And the other 3 referees were all very enthusiastic and said, definitely publish it. And in fact, one of them was Sean Carroll, who identified himself. So the paper got an editor's recommendation, and they commissioned Steve Carlip, the well-recognized, well-regarded quantum theorist, quantum cosmologist, to write an article about it. So that was so far as I know, I'm not aware of any other example of a paper where it's shown that there can be a perfectly good arrow of time that comes straight out of the fundamental equation. It's there. And it's getting more and more citations. I think about, on average now, at least every week, I get a notification from either Academia, EDU, or ResearchGate saying somebody's cited that paper. So it is being cited now. Yeah. So I think personally, well, I just want to finish. I believe that just completely changed the whole discussion about the arrow of time.
Mm-hmm. Well, then, just to wrap up this portion of the discussion so that we can move on, so the portion on thermodynamics, and perhaps to summarize some of what we've discussed so far, in a nutshell, why ultimately does the discovery, development, the subsequent understanding of entropy remain insufficient for substantiating time's arrows? And then we can move on to some of the chief points of that's kind of redundant, of the Janus point.
Well, I think all of the arguments which say, it's what I've already said, all of the arguments which say that time's arrow is determined by the growth of entropy is just only applies. You have, first of all, to assume that for some inexplicable reason you start off with a very special ordered state, and that state is confined, it's in a box, and it can't help equilibrating, and that will create an arrow of time. Then you look around at the universe and you see that it's way out of equilibrium. And when you then look at what Newton's theory of gravitating particles tell you, then it's no mystery at all. That theory tells you the universe will seem to have started in a very uniform state and become structured from then on. That's just sitting in Newton's theory. And I think this is bound to change the whole discussion.
Mm-hmm. Yeah, I think that was a very helpful summary. So in the Janus point, you propose 2 main changes to the current thinking about time, but the first is the title of the book, which we haven't discussed at all yet. So what, at first blush, is the Janus point, or a Janus point, since that's more general?
So the Janus point goes back to what's called the first qualitative result in dynamics. This is a discovery that the great French-Italian mathematician Lagrange made in 1772. He published a very, very famous and magnificent paper on the 3-body problem and more than the 3-body. The 3-body problem is the problem of the Earth, Sun, and Moon under their mutual gravitational attraction. And he showed for that system exactly that if the energy is either zero or positive, then in the distant past, the size of as measured in the Newtonian theory, the size of the universe is infinitely great. Then it decreases monotonically down to a finite minimum value, and then it increases monotonically to infinity. And that minimal point is what I call the Janus point. Because you could imagine the Roman god Janus standing at that point and looking in either direction and seeing the universe getting larger. And so it would be like a child growing. Where he's standing, the universe is smallest, and then he just goes on and becomes a giant. Now, however, that's presupposing a scale, a ruler outside the universe. So, in fact, any intelligent being within the universe couldn't see its size growing like that. It would need to see structure changing. Now, what is very interesting is that in Newtonian theory, there is a quantity which measures how clustered it is. So I guess everybody who's interested in watching this will know about first of all, the Newton inverse square law. That's where the gravitational forces depend inversely on the square of the distance, and they're derived from something called the Newton potential, which is inversely dependent upon the distance between the two particles. And so the Newton potential, you take all pairs of particles, you multiply their masses, and you divide by the distance between them. And then you add up all those quantities at a given configuration that the universe has, and that gives you what's called the Newton potential. And that depends upon a scale because it's 1 upon r. So to actually measure that, you'd have to be outside the universe and have a ruler to measure those distances. Now, you can get something which is observable within the universe if you multiply it by something which cancels that 1 upon r by something which depends upon the distance, r. So you then multiply something which depends upon r by something that depends upon 1 upon r, and you get something which doesn't depend upon the scale. And that's what the n-body specialists call the shape potential or the normalized Newton potential. And in fact, it is what really determines the Newtonian theory of gravitating point particles, especially if you're treating them as a model for the universe. It's not the Newton potential because that's so to speak, not intrinsic. It's not really telling you about the universe. It's telling you how something in the universe is related to something outside it, but there shouldn't be anything outside the universe. So this quantity, which we then called the complexity, and we introduced this word in our paper in 2014 in Physical Review Letters, this is very fascinating because it's a positive quantity and it has an absolute minimum. It has an absolute minimum when the shape is as uniform as it possibly can be. And if you have just 3 particles, whatever their mass is, that shape, the most uniform shape, is the equilateral triangle. Lagrange knew this. And then it can be it can, if the universe gets more structured, this quantity gets larger. As the universe gets more structured, it gets more larger, and it measures the growth of structure. Now, when you look, with my fingers, I illustrated this idea of the Janus point and said, well, this is the scale growing. But what is really the thing that you can observe inside it is at this point, at the Janus point, the distribution is most uniform. But as you go away, structures form, isolated systems form, things like solar systems or even galaxies or star clusters. These can form, and they do in Newtonian theory, and that's structure forming. And that this, if Janus stands at the Janus point and looks in both directions, he'll see that it starts off very uniform at his feet, and as it goes out, all this structure forms. And in addition to that, among those structures that form, particularly interesting, are what we call Kepler pairs. That's 2 particles going around each other in Keplerian elliptical orbits. And they do that with ever better accuracy. And as they do that, their period is the ticking of a clock, the length of the major axis is a ruler, and the direction defines a compass direction. And all of these Kepler pairs are doing that together, and all their behavior is synchronized together. It's a fantastic creation of order out of disorder. And those Kepler pairs, those clocks, they only form precisely because the Newton potential has that 1 upon r dependence. It doesn't form. Newton knew that there are only 2 potentials that can have closed orbits that would define clocks. One is the Newton one, and the other is the one that Robert Hooke had discovered. That's the elastic one, but that's a repulsive force, and clocks don't. It's only with difficulty you can get that to form clocks, and they don't have this wonderful behavior. But the Newtonian ones, the Kepler pairs, they can have all periods, all sizes, all directions, and they all come together, all fantastically synchronized. This is just something that people who study Newtonian theory, the great bulk of them are completely unaware of this. But it's an amazing inversion of the way that one should think about Newtonian theory. So, I mean, the poets like William Blake hated Newtonian theory because he said it's a theory of clocks endlessly going round and nothing interesting happening. Because basically that's a little bit what the solar system looks like, although the solar system in reality is vastly more interesting than William Blake thought. But in fact, what Newtonian theory is not a perpetual theory of cogs, turning forever. It's a theory of the creation out of uniformity and disorder of incredible order in the form of these clocks. And with the other forces of nature, I believe it is actually gravity and the other forces is actually creating the structure that's enabling you and me to talk now. And this is a complete inversion of the standard story. And it's at least made plausible by the Newtonian theory. Now, we're way from developing this into a full theory of how you and I can be talking to each other. But I think it's an encouraging start, at least in Newtonian theory. And certainly the major force that is creating structure in the universe is gravity, and it's described extremely well by Newtonian gravity. Einstein's theory only makes a small correction to the fact that gravity creates structures. I mean, Einstein's theory is important for black holes and things like that, but the creation of structure is, to a large extent, can be understood by Newtonian gravity.
Well, we're certainly getting into the weeds here now, and so there are some things that I was hoping that we could clarify a bit. And starting with one thing that you mentioned at the outset of your response, but because size can mean many things, when you refer to Lagrange and the size of the universe going from infinite to finite and then finite, are you referring to mass or volume of the matter or volume of absolute space, which I presume you're not because of your appreciation for Ernst Mach? But what do you have in mind when you're talking about the size of the universe?
Well, that is that there is, so to speak, an invisible ruler which measures the size. I mean, Lagrange was not challenging Newton. I mean, basically, Newton was challenged by various people in his own time, by Leibniz and Huygens and Bishop Berkeley. They all reacted to Newton's against Newton's idea, and then in the 19th century, Mach repeated these criticisms. But Lagrange wasn't concerned with that. He was doing just purely mathematical work to understand how the solar system worked, and he clearly presupposed an absolute ruler, that there was, so to speak, that, I mean, it is so easy because the fact is there's always something either bigger or smaller than us, and that just leads us instinctively to think that there is some notion of distance without there being a ruler there to measure it. But the reality is, if I want to, measure the width of my head, I have to pick up a ruler, but I see it's gone from my study. It's down in the kitchen, or I can say that my hand is extends further than my forehead, and because you can always do that, you instinctively think there is distance there, even if everything disappeared. But this is the sort of mistake that Leibniz and Mach particularly said you mustn't make. And I think there's a huge change possible when people really shake off that way of thinking. And in fact, actually, it definitely was behind that paper in Physical Review Letters, because I had read Leibniz's philosophical writings in 1977 and had been hugely impressed by him pointing out that if there was no variety in the universe, we could say nothing. So I was, and in fact, in his monadology, he says that we live in the universe which is more varied than any other possible universe, but is subject to the simplest possible rules. And that made a big impression on me, and equally on Lee Smolin when I introduced him to Leibniz's writings. So I'd always been on the lookout for something that would measure variety. And in fact, my only paper with Lee Smolin is about a mathematical idea that a mathematical model that Lee had developed. And we have one paper which starts with the title Maximal Variety. But as the time went on, I felt that Lee's mathematical idea, although very neat, was not actually going in the right direction. So I was looking out for something that would measure variety. And around about 2010-11, talking to very good specialists on Newton's theory, I discussed it. This was at the observatory in Paris. I came to the conclusion that this quantity which I've mentioned, which we call the complexity, but the specialists call the shape potential or the normalized Newton potential, was actually a good thing to measure of variety. And that then a year or two later was what led to the paper in PRL. So there's no doubt that this idea, which I will stick my neck out and say, nothing is ever definite in science, but that paper of ours has changed the discussion about the origin of the arrow of time. It shows that you don't have to appeal to a past hypothesis. There may be a perfectly natural explanation which comes straight out of the known laws governing the universe.
I have a broader, perhaps, I don't know if you'd want to call it a naive question, but a general question. So this is, as you've mentioned a number of times, a major departure from conventional thinking about time, in which there is one direction, really. Now we have a point from which there are two directions, from past to future in one direction, and from past to future in were you going to say add something to that?
So, first of all, those were the solutions which Lagrange knew about, and they are what I call bidirectional arrows of time. So they go out in both directions. Now, Lagrange published his paper in 1772. Now, another 125 years later, other solutions of Newton's theory were discovered, which are extraordinarily interesting. And it's again this quantity, the complexity or the shape potential, which is decisive. So they're known in n-body theory as total collisions. So in these solutions, all the particles the shape that they form changes, but it becomes what's called a central configuration, a very special shape. And when it reaches that very special shape, all the particles collide together at their center of mass. That's called a total collision. And the specialists have found no way to continue that solution uniquely. So it's regarded as a breakdown of Newton's theory. The equations break down there. But now by time reversal symmetry, you can reverse that and say that it's a Newtonian Big Bang. The particles all start off and that special state, that special shape is generally very uniform, and it can be the most uniform shape that the universe can possibly have. In the three-body problem, it is the equilateral triangle, which is definitely the most uniform. So in this case, instead of having bidirectional arrows going out from a Janus point in both directions, you just have a universe which begins in its most uniform shape and then just goes on getting more structured forever after. So it's like half of my Janus point solutions. So in a way, if I'd known, I mean, my book proposal to write the Janus point was, it went to the publishers out from my agent in the autumn of 2016. And at that stage, I wasn't really taking very seriously these I knew they existed, but I wasn't taking these alternative solutions very seriously. So I proposed a book to be called the Janus Point, and my agent thought it would go very well, and it did. I got quite good royalties, and so did the publisher. I mean, the American publisher thought it would do very well. In fact, as of now, it hasn't sold so well. But it's getting, what is more rewarding for me is it is getting more serious scientific attention than my earlier book, The End of Time, which did become a bestseller. I mean, that's still selling, a useful number. I just get, today I checked my bank account and I see £100 has come in from royalties on that. And that was published 24 years ago. So it's bringing in a few pints of beer or something. But if I could ever write another book now, I probably wouldn't call it the Janus Point. I'd give it some other title, because I now think that these alternative theories are much, much more interesting. And I am already talking about that. You'll have come across that in the chapters 16 to 18 in the Janus Point are about these. Yeah.
Right. So the half solution stemming from collisions does seem much more germane to the lay.
I would say they're big bangs, because I mean, the way they were discovered as total collisions, but by time reversal symmetry you can make them explosions, and that's how I interpret them. And because they start very uniform and then get more structured, and that matches the cosmological arrow of time. The cosmological arrow of time is that the universe started extremely uniform and has got more structured ever since. So it matches very well the known history of the universe. Now, whether it matches the fine detail, whether we can develop a theory which matches the fine details, that's another matter. But in broad details, it matches very well.
Yeah, so maybe I should say the half solution stemming from considerations of collisions, but then looking at them through the lens of time reversal symmetry. This seems much more germane to the lay understanding of the Big Bang. But for now, at least, if you'll humor me, just restricting ourselves to this conception of the Janus point, where there are two half solutions stemming from a common past, each moving in different directions towards distant futures. The concept seems like such a huge leap from what is currently considered canon that it has to be super powerful what it can account for to motivate it. Sort of like, and I gather from talking to people like Sean Carroll, this isn't how they think of many worlds, but many worlds, for me at least, has to have some serious pluses to motivate such an inflation of ontology and all of those many, many worlds that it suggests exist. And yet the second wing of the Janus point, again in this two half solution construction, can't be observed. Am I right about this? That there's nothing about the present there's nothing from the present that can allow us to recover in any sense what's happening or has happened or will happen in their future on the other side of the Janus point?
No, by the way, it's not the fact that there's two half solutions is really not the correct way to say it. There's only one solution. It just has a special point along it. It's just a single solution. There's nothing remotely like a collapse of a wave function or something like that. They're qualitatively similar. They're not identical, and it's just the significance of the Janus point was just that it showed that you could get an arrow of time without a special condition that had to be put in by hand. It would be very interesting if Richard Feynman could be brought back from his grave and have this discussion with him and put him right, so to speak. It just is that you can get an arrow of time where he said, this is utterly mysterious. We just have to add something to the known laws of nature. You do not have to do that to get the arrows of time. And it just happens that we first of all Lagrange discovered this situation, but without this looking at the complexity that came. That's something that's come much later than Lagrange. But the mere fact is there, and it's all just one solution. It's just that you must think of a timeline, and there's just as you go along the timeline, it just gets more structured in both directions away from a most uniform point. That's the way to think about it.
Right. So I wasn't trying to say that there's a striking similarity between the two directions branching off from the Janus point and wave function collapse, just that both theories have very unintuitive consequences relative to our manifest understanding of time or macroscopic phenomena. And because of that, we would want them to be very powerful to account for otherwise anomalous phenomena like the direction of time or wave function collapse.
So in a way, of course, it will be much better. This was really getting more and more clear to me as I was writing the Janus point, that these solutions, what I call the Newtonian Big Bangs or total explosions, are much more attractive. So the test of our ideas will be if then we can develop it into a theory which can match general relativity and matches precise details. There are very precise. The real test of our ideas, if they really can be developed, is in the information from the cosmic microwave background, which is very precisely measured, its properties. Now, if we can reproduce that and say that must be there and doesn't require this, what is looking increasingly unsatisfactory, the theory of inflation, then we'll be in big business. But that's, I don't anticipate that happening in my life. It would be nice if it does. But at least I can see the possibility of it.
Inflation is something that I would also really like to get to. But before that, and maybe this is something that you don't want to talk to, since you said that the aspects relating to or stemming from collision that look more like the Big Bang is much more interesting to you than the twin solution, or the one solution with two branches from the Janus point. But can we talk a bit more about the twin branch version?
Yes, sure, yes.
Okay, so we have, and this goes back to something that I already mentioned, but we have records of the past on our side of the Janus point that convince us the past is real. And is there any, or could there be theoretically any evidence of the other side of the Janus point when everything in its past moves further away from us, or everything in its future moves further away from us?
Well, if that were the right story for the universe, which, as I say, I now really don't think is the case, but if it were, it would rely on very precise confirmation of predictions that a development of the theory would make. I mean, one begins to believe in a theory when the accuracy with which predictions are confirmed runs to 8 or 9 decimal places. This happens in quantum field theory now, for example. They make calculations of the anomalous magnetic moment of the electron or whatever it is, and it comes and they keep on pushing the calculations ever further. And I'm not an expert in that at all, but they've got to about 9 or 10 decimal places in a pure number. And in fact, I was at a workshop in Germany in February, and they were talking about optical clocks, which are and will be phenomenally accurate. And the speaker who was talking about them said, "I'm now going to tell you about the most accurately confirmed law of nature that has ever been confirmed." And what it turned out was he was just talking about the ratio of two frequencies that these atoms emit and the corresponding wavelengths. And it's just the ratio. That's a pure number, just the ratio of that. And I think from memory, he said this was now confirmed. This was now theoretically and observationally confirmed. I hope I'm getting this right, to 11 decimal places or something. And he said this is the most accurate confirmation of a law of nature. So we would have to be getting to that sort of accuracy. I'm beginning to hope we might get to 2 or 3 decimal places with some interesting things we're discovering in the Newtonian theory. But already that would be interesting because it would come out of some completely new way of thinking about things. But that's as yet an aspiration. There's nothing secure about that yet.
Well, early at the beginning of our discussion, we talked about entropy and its etymology, and I mentioned this neologism entaxy that was coined by your collaborator Flavio Mercati. So, and now I think is a good time to discuss that. So, what does it mean that the arrows in your theory that correspond to entropy point toward structure rather than to disorder? And you've talked a little bit about structure, but then also how does this relate, going back further again, to Boltzmann's intuitions about entropy providing a basis for the arrow of time?
Well, it's just this huge difference again. I mean, I just always summarize it. Are we talking about a system in a box, or are we talking about a system which is not imprisoned in a box? And certainly the theory of Newtonian particles interacting with each other, which seems to be a pretty good model for the way the whole universe works. They're not in a box, and it is the exact opposite. I already said if the system is in a box or not, the difference is the difference between black and white or night and day. If they're in a box, it's entropic and it's heat death. If it's able to do its thing without any restriction, it can do what it wants, it will create structure out of uniformity. That at least is exactly what happens in the Newtonian theory. I think I'm fairly hopeful that if we add electrostatic forces, we'll see the same thing happen there. Now, this is a long, long way from a complete theory of the universe, but it definitely changes the whole discussion about the origin of the arrow of time and gives a very plausible reason why it should be utterly different. It's just whether or not the system you're talking about is in a box. And given that you can search all the literature you like on thermodynamics and on the arrow of time, you won't find people making that point. You will find the great Gibbs and also Boltzmann. There's a brief remark by Boltzmann at one stage. So Boltzmann was struggling in this. There was a famous debate between Boltzmann and the man who later became a famous logician, logician, Zermelo in 1896, where they struggled. They were talking about what's called the Poincare recurrence theorem. But the Poincare recurrence theorem requires essentially the system be in a box or to have a bounded phase space. And Boltzmann in that debate says, are we so sure that the universe is in a box? Well, I'm putting his words in mine. I'm putting my words into his. Are we so sure the universe is in a box? But in 1896, nobody had really much idea about the universe, and they certainly didn't know it was expanding. So that came nothing. But if you then there's this very, very fine book by Willard Gibbs, published just at the end of his life, 1902, 1903, where he develops this wonderful theory, which is still the solid foundation of statistical mechanics. This comes the really solid and best foundation comes from Gibbs. And he develops all the mathematics, and he develops a theorem called the conservation of probability, the Liouville measure. And then he says, but I must put in a caveat. All of this will not hold. None of my probabilistic arguments will hold if the system can expand into infinite space, or if the energy and momenta can grow without bounds, because then the whole probabilistic arguments just fail. But he doesn't say what is likely to happen in that. So it's quite clearly in Gibbs's book. But again, I bet there's jolly few books on thermodynamics and statistics which mention that fact. I haven't looked at all of them. I've just looked at a few.
Right. So Poincare recurrence, this notion of, or this question of whether or not the universe is in a box has recurred many times throughout our conversation. And a few minutes ago, you mentioned inflation and problems with inflation. And this makes up a substantial, maybe a chapter or two of the Janus point. But for those who aren't familiar with the notion of inflation, what is it? What important empirical phenomena does it explain? And what are its lingering problems that you were alluding to that leave an opening for an alternative proposal?
The problem of inflation, I guess the history of it comes in around the late 1960s. This is after the microwave background. So cosmology was completely transformed by the discovery of the microwave background in, 1964, 65, that there is this radiation at about 2.7 degrees centigrade, very absolute Kelvin, 2.73 Kelvin. Very, very low temperature. But there's thermal radiation all around us. And it had been predicted, and it was found by accident. And that completely transformed cosmology. And the picture that then developed, the simplest model of cosmology, predicted that the universe would be completely uniform, that it would be born completely uniform. There would be no structure in it at all. And without structure, you could not have the formation of galaxies and things like this. So there were two very important papers in one in 1968 by an Englishman called Harrison, who had moved to the United States. And it was followed by, 2 years later, by the Russian Zeldovich, with saying, there's a problem. We don't know where the structure would come from, but to create galaxies, the structure would need to have a particular form. Well, it's called a scale invariant potential. So the question was, where could that come from? Where could that structure come from if it wasn't really there in the start? So that's the birth of the problem. And what then happened was Alan Guth, in his doctoral thesis in I guess, was it from about 1975 or something, he was working on things in particle theory where there was a theory that magnetic monopoles should exist. These were very sort of exotic things. And the theory that existed at the time suggested they should be all over the place, but there was no trace of them to be found anywhere in any experiments. Nobody found anything. And Guth realized that there was a special type of force which could make the universe expand incredibly fast. And so he thought, this could explain why we can't see any magnetic monopoles, because their density has been greatly reduced. And then there was another problem which Bob Dicke, he was the person who had predicted that the microwave background would be discovered and was about to build a machine to detect it when it was found just up the road, about 30 miles away from him at wherever it was. Dicke was in Princeton. I can't remember where the discovery was made of the microwave background, but Dicke had pointed out what's called the horizon problem. So the microwave background had an incredibly, it still does, has a very uniform temperature wherever you look in the universe. It's thermal equilibrium to a very high degree. But the then existing theory of the expansion of the universe showed that if you went back, the universe would never have had any opportunity to equilibrate, to get into thermal equilibrium. So this is called the horizon problem, and it is still sort of there. I mean, somehow or other, a theory's got to explain why the microwave background has the same temperature in every direction. Just the mere fact that the temperature was the same, twice the moon's diameter or something like that, was a major problem. So Guth then thought, well, maybe the universe did have a chance to get equilibrated right at the start, and then was also producing these magnetic monopoles and this ability to expand the whole universe very fast. And then that would solve two problems at once, kill two birds with one stone. So he then, in I think it was 1980, he published a paper where he coined the expression inflation. And then in 1982, there was a very famous workshop in Cambridge in England, which a lot of really significant people, including Stephen Hawking and others, were present, and Guth presented his ideas. And then they realized that in a very rapidly expanding universe, if the right conditions were, you still had to have the right conditions at the start, you could get these Harrison-Zeldovich fluctuations to be created as quantum fluctuations. There's quite a lot of technical stuff going into all of that, but the very rapid expansion was an important thing, and then it had to start. And in fact, Paul Davies, who's a very solid scientist, and his student Bunch had established that there could be a particular, they'd found that in de Sitter space, one of the solutions of Einstein's theory, you could have a vacuum, which is now called the Bunch-Davies vacuum. And then it was found in 1982 that this very rapid expansion would transform the Bunch-Davies vacuum into Harrison-Zeldovich fluctuation. That's the broad picture. So this was seen as a huge success, and there was huge excitement because it seemed to suggest that quantum theory would explain the huge macroscopic structure of the universe, why the stars and particularly why the galaxies are there. So this was hugely exciting. However, it did require sort of fine-tuning. The conditions at the start had to be right, and so they introduced something called an inflaton, which had to have rather special properties. And I remember going to lectures in Oxford in about 1992, so about 30 years ago, where the speakers had made it very clear, look, inflation is an unsatisfactory theory, because we don't have a first principles theory of what is at the start, what is the inflaton, and how does the expansion all get started. What happens, he said, is quite clear. We make observations now, and from the observations now we say what must have created them. But that's just putting the answer in, getting the theory out of the answer, not having a theory and then getting the... I mean, this was so different from Einstein's theory, who in 1915 he'd predicted that the light deflection of stars light from the stars passing the sun would be exactly twice what Newtonian theory predicted. And that's what Eddington confirmed in 1919 and made Einstein a world celebrity overnight. There's nothing like that in inflation at the moment. And I think it's, although I don't engage in intense discussions about this, but sort of just following the things, I think an increasing number of people are getting worried about inflation and saying it's a bit tricky. And then there's a significant problem how it all gets started, because although the great thing is that it's changed. The story has changed a bit. Now you have to have a part of the universe, a certain amount of the universe, which is initially uniform for it to get going, and one doesn't know how it starts. So I don't want to be taken for a world expert on this, because I'm not. I just listen to what people say and pick up things and read the odd article. But I don't think I think it's a common view among quite a lot of people that inflation is getting a bit problematic now. So that's it. But what I'm saying in the Janus point is that if the Newtonian theory is any guide, at least in these Big Bang Newtonian solutions, which, by the way, the theory was incredibly beautifully developed in a paper published in 1918. That's 11 years before Hubble published his result on the expanding universe. The whole theory of the Newtonian Big Bang was developed in most marvelous mathematical detail in 1918 by a French mathematician called Jean Chasset. And that suggests that the Newtonian Big Bang starts very uniform and then gets structured. You don't have to put in uniformity, and you don't have to put in inflation. You don't have to put in anything. You just take those Newtonian solutions and do it. Now, when I talk about this, no experts are taking me particularly seriously. Some of them do they are interested. But the acid test is to get the fine details right. You have to get what. So Harrison and Zeldovich said that you have to have a diagram, a spectrum which rises linearly with a slope exactly 1. But then it was suggested that the slope might be slightly less than 1. Instead of being 1, it might be 0.95, 0.96. Well, this, in fact, is exactly what is observed. The slope is slightly less than 1. So that would be the absolute acid test. But now, if that came out of this Newtonian theory, which it might just do, I think it's not impossible that calculations on a supercomputer, and I am talking to two people who might be able to do these calculations, it might be possible to show that if you had a Newtonian universe with trillions of particles, that very precise structure with a slope just slightly less than 1 is sitting there. If that would come out, that would be impressive. But this is in the future. It would be nice if it comes. But certainly the Newtonian theory suggests it might be possible.
There's a terminological distinction that I think you're making, but that I'm not familiar with. So obviously when something inflates, it expands. But expansion, as I understand it, and as observed by Hubble, I think is very well confirmed. So just what is the distinction between expansion, which is confirmed and accepted, and inflation, which is being questioned?
Well, first of all, I think both Hubble, the normal way people think about Hubble's discovery and inflation, I think there's still definitely an instinctive feeling that there is a ruler outside the universe. I think there's a lot. I think this is. I was on a radio program in Britain called In Our Time with Martin Rees, who at that stage was the president of the Royal Society. He's a very distinguished astrophysicist and a great scientist. And we were talking about the expanding universe. And I stuck my neck out and I said, for me, the expanding universe stinks. It's not expanding, it's changing its shape. And Martin was really quite taken aback. He said, Julian, well, your philosophy might be quite interesting, but I think you're forgetting 95% of the physics. I'm actually getting much more confident now that I was right. It just was that I needed to, I can flush things out better now. So what the situation now is, and about this I am confident, is from the known history of the universe, more or less the first structures that actually formed were nucleons. This is very early on. So nucleons formed, then atoms formed, and then molecules formed, and then stars formed, and then galaxies formed. Now, all of these things, once they'd formed, the sizes that they had, the ratios of their sizes stayed more or less constant. So these are all, so to speak, mutually consistent rulers. And the one thing which changes is the separations between the galaxies. So you can use all of these things, starting with nucleons, atoms, you and me, the Earth. There's a whole lot of things whose sizes have not changed significantly for billions of years. But the one thing that has changed radically is the separation between the galaxies. And that is actually, it's just really, strictly speaking, it's a change of shape. It's become, the shape is defined by ratios. It's the ratio of all those rulers to the separation between the galaxies. So I'm pretty confident I was right to tell Martin that the universe is not expanding, it's changing its shape. And this is the only thing in physics that has meaning is a ratio, and people just forget this. Now, I have a collaborator who's a cosmologist. I won't mention him because he may not want me to do it, but he says that when cosmologists give lectures to students, they start off by saying, well, we can't really talk about the size of the universe, so we say that the size of the universe now is 1. That's a nominal definition. And then its size in the future is some ratio of that, or its size in the past is some ratio of that. And then he says they forget all about that statement. Just instinctively think that there is, that the universe is, that you can speak about size of the universe, whereas really it is always ratios. It is always ratios, and people just forget this. I mean, as I look at you, if I just look at you now, your head is and the cat is a fraction of the picture behind you on the wall. These are objective facts, and you can never. Science is never get away from that, and it's just staggering to me that a large number of cosmologists and physicists and so forth just forget that fact.
So, to help me better understand then what you mean, for what would it take for you to say that the universe is expanding? I know that the first law of thermodynamics is that energy is not created or destroyed, but would you say the universe is expanding then if more mass were added to the universe? Is that the sort of thing that would make you say that the universe is expanding? Or is the universe just the sort of thing that can't expand based on your terminology?
I think it's just meaningless to say that. I think the universe is changing its shape. It's just getting more structured. Yeah. That period. That's it.
Okay, well, so we're getting to the point where we're wrapping up, but there was one lingering question that I had that you said we might get back to later in the discussion, but it didn't come up. And that was earlier on, I think the first time I mentioned Hugh Everett and Many Worlds, you said you've become increasingly skeptical. Maybe it was increasingly skeptical not just of Hugh Everett and Many Worlds, but of there being a wave function at all. And you said we might get back to that. And maybe we could talk about that for the last few minutes.
In the Janus point at the end of chapter 18, so there's been this huge problem in quantum gravity as time has disappeared. Back in the 1960s, somebody called Bryce DeWitt wrote down an equation for what the wave function of the universe would be, and it seemed to suggest the wave function of the universe was static. It just didn't change. There were just, on the face of it, there were just probabilities for configurations of the universe, and that's called the problem of time. And for close on 60 years now, people have been trying to solve that problem, and they've suggested that the mistake, and I'm sure it is a mistake, was to think that there was an external clock, just as many people still instinctively think there's an external ruler. The Newtonian time in which quantum mechanics was formulated was an external time, and they pointed out that really you always tell time by looking at something that's moving. You look at the moving hands of the clock. Here it is. Here's my clock. The hand moves, and you can tell time by looking at something moving. So then the idea was that there's lots of different things changing in the universe. The change in the universe is undeniable. So they said, well, you must take one thing that's changing, call that time, and then see how the others go relative to it. And that's people like, well, lots of people have done that. Carlo Rovelli has argued strongly for it, and others. And so in the Janus point, because so at the end of chapter 18 of the Janus point, I made a proposal which was exactly along those lines, very conventional, except that it was novel in that none of these earlier proposals had suggested that time is actually just the shape of the universe as measured by that complexity it requires the universe to have a finite number of particles, but that quantity, the complexity I defined, which is just the Newton potential made scale invariant in the way I described, that could be time, and it would be just like the date stamp on a coin. It would also be the age of you then would go straight from the minimum value of that complexity would be the birth of the universe, and then the complexity at now would be its age. The difference, you take away what its absolute minimum is, and that would be the age. And as the universe, so I would now think, and also my collaborator Kozlowski thinks that very much, where we talk about the complexity defining the age of the universe. And that fits very well, because in a way, it's like me getting a bit more crinkled and my hair getting disordered as I get older. That's a measure of my age. I mean, you look at any human being, and it's not difficult to get a fairly good estimate of their age. And that just does match what the universe has done, really. It started very uniform like a baby's bottom, and now it's got structured like our faces and things like that. So it's a very attractive idea. And then what is very interesting, and this is to do, so the key concept that, this is my baby, I coined the concept of shape space and shape dynamics. So shape space is the space of all possible shapes that the universe could have. And if it just consists of three particles, it's just the shapes of all possible triangles. And they start off with the equilateral triangle, and then they become ones where one particle is over there and two are here, and it's a very pointed triangle. And from that you can define the complexity. So that was my idea. That idea is novel to me. But then what is really interesting is that in shape space there is something which is called a probability measure. So there are, in the Janus point, I have pictures of what shape space looks like, the shape sphere when it's only 3 particles, and you can represent the possible shapes of a triangle on the surface of a sphere, and you see that it's just a finite sphere. And then you can literally work out probabilities. It's because shape space is what's called compact. You can give it a finite volume, and then smaller volumes within that are fractions of the total volume, and then you can say there are probabilities for that. So this is something which is not possible in ordinary cosmology because it still has got that original sin of an absolute ruler sitting in it. So what is very interesting is that you can define probabilities for shapes at a given value of the complexity, and this is completely new, and that's very surprising because I proposed a wave function, a wave equation like the Schrödinger equation for my idea of time, but I saw straight away that it would have a unique solution, so that sounded very good. But then my collaborators realized that it was very special because there would be equal, on the face of it, there would be equal values of the wave function for at a given time, with time defined by the complexity. Each shape at that complexity would have the same value of the wave function. But because there is what you could call a probability measure on it, you still have definite probabilistic predictions. So we would have something which is, so in quantum mechanics, there's something which is called the Born density. The Born density tells you the probability. You have a wave function which you get from solving an equation, and then you look at what's called the Born density, which is in that, and then that tells you the probability of finding something. So what we were getting was this famous something like this famous Born density out of very, very basic fundamental very simple basic geometrical considerations. We were getting a Born density for shapes of the universe without any wave function. So this is quite, so that's on, there's a 3-page paper by me, which I wrote for David Deutsch's 70th birthday. It's got the title Quantum Without Quantum.
You sent that to me.
Yeah, I sent it to you. And in that, there's, in reference 4 in it is to 2 talks I gave. Well, one is a talk I gave in Oxford to the Philosophers of Science in May last year. And the other one is to a more recent podcast by someone called Vasudev Sham in Stanford or Berkeley or somewhere, in which I explain these things. So if you're, and that's on the archive, and I think it's on my website, platonia.com. So this was a completely unexpected development, but it follows with great necessity. Now, rather interestingly, this is an interesting thing. Lewis Carroll, Charles Dodson, who was a mathematician and wrote Alice in Wonderland, he claimed that he could prove the following. He said, given any 3 points in an infinite plane, I can tell you what is the probability that it will be an obtuse triangle. In other words, one of the angles will be more than 90 degrees. And in fact, he was wrong because you don't have enough information to make that prediction. But that's exactly what this thing we can do in shape space, because once you fix the complexity, then you get a contour on the shape sphere. You get contour lines of equal values of the complexity, and then you can just say what is the probability that the most acute angle is less than, say, 1/6 of pi? And you can just work it out. You can actually see it on the shaped sphere. You can literally see the solution to Dodge and Lewis Carroll's problem when it's properly formulated. And that's, well, we'll see. Anyway, but that's secure mathematics. Whether it's the right physics is another matter. But I did send this note to a very distinguished professor. I won't say who it was, but he's a very friendly and nice man. And he wrote back, Julian, I react with disbelief. I think your proposal is the greatest exaggeration on the basis of a very small amount of evidence, although I must admit the evidence is very interesting. So I wrote back to him, well, thank you very much for being, so saying, I shall persevere. I think disbelief is not disproof, so we'll see. But whatever, I mean, if it's wrong, it's still right. It's still interesting. It is a very interesting thing. There are very interesting. I don't think there's any doubt, and there's more in that little note. Extraordinary structures sitting inside Newtonian theory, which were discovered by a student in Paris, Manuel Izquierdo, after we'd made these ideas. So he then found extraordinary structures, which are quite new. Nobody had known that they were existing in Newton's theory. So that's all in that little note of mine. So anybody who's watching this, go to the archive and look for my paper, Quantum Without Quantum. You can share the opinion of this very distinguished physicist that it's a ridiculous, exaggerated speculation on the basis of little evidence, but it's thought-provoking, at least I'm sure.
Well, Julian, this was so much fun. I've wanted to talk to you for such a long time, especially because so many people have recommended that I have you on the show. So thanks so much for joining me. Thanks so much for writing the Janus point, and thanks so much for having this conversation with me.
Okay, all right. Nice to chat. Okay, bye then.
Hold on, Geeslings. Before you go, please like, subscribe, follow if you haven't already. Smash all those buttons. And also, if you haven't followed me on Twitter at Robinson Erhardt, or if you're not joining me every morning as I eat my pint of ice cream on Twitch at Robinson Erhardt on Robinson Eats, please do so.